to modeling growth. And as I described to you before, I got this long digression into Schumpeter destruction, creative destruction. There was already at the time of around 1700 Robert Malthus, but this kind of tradition continued, and there were a series of Nobel Prizes related with this theory of growth, which basically says that the capital, in the case of Malthus, it was the population, at time t+1, let's say 1 year after waiting 1 year, you get what you had before, plus a certain quantity which shows what is the balance of birth and death in that population, or the balance between production and depreciation in the case of the wealth of a nation, which basically is measured by GDP. Though the way GDP is computed is in such a way that even if actually the country is not producing much and is losing a lot, the GDP is formally still positive. So it's a little bit misleading, but we'll see that there are bigger problems with this kind of formula. So I hope that instead, in spite of the fact that this is a formula, you will not consider this as high mathematics, and you'll bear with it, because we really need something to be precise. In general, the introduction of mathematics in different models and understanding things is in order to make it precise. In fact, in economics, they are not able in general to predict anything and to compute anything about which is useful for making predictions. But at least the use of mathematics allows them to make very precise what they mean. So when they argue with one another, it happens less often that whoever says something can have otherwise after that say that, well, I didn't really mean that. If you express it in a mathematical formalism, it's more unambiguous, which is a good thing. So as I explained many times, if you multiply K, suppose that in place of 1 year you wait 2 years, 3 years, then each time, if A is constant, then each time you multiply by 1 plus A, which it's sometimes written 1 plus A to the power T. 1 plus A to the power T, it only means that it's 1 plus A times 1 plus A times 1 plus A T times, that's all. And if A is bigger than 1, then of course multiplying by a quantity many times by a quantity bigger than 1, then that quantity increases. And in fact, almost by definition, that kind of growth, it's called an exponential growth. And I feel a little bit easier to speak about it because with this story of Corona, exponential growth it's invoked very often, and A essentially it's in the case of Corona, it's essentially the coefficient of contagion. So if, or rather 1 plus A is the coefficient of contagion. So if you get, if the coefficient of contagion is less than 1, then fewer and fewer people are contaminated, while if A is bigger than 1, then more and more people are contaminated, so there is an exponential increase. If A is negative, then it's an exponential decrease. And already, maybe I feel very much inclined to emphasize to you that this little arithmetics which I'm doing, it's very justified in the sense that it characterizes, as you see, just almost without my intention, just by telling the story, it tells the story of population growth, like in the case of Malthus. It tells the story of economic growth, like in the sense of Arrow, Romer, and Lucas, which got Nobel Prizes basically for this kind of models. And it tells the story of contamination in corona or in other diseases. And of course, it's also the same kind of mechanism happens with viral spread of some little movie on the internet or on the YouTube or some fake news or things like that. So so this kind of dynamics, this kind of evolution is very generic, and this is what I'm teaching it, and this is why when I announced the course, I said I'm going to describe crisis, economic crisis, and epidemics and whatnot, and it looked maybe a little bit overstating and ambitious, but as you see, they are all of them more or less the same thing. Once you understand one of them, you understand the others. However, I explained to you in a previous lecture that this naive model in which A is, there is one A for the entire country, it's not correct. So in this sense, we have seen with the corona that there were some regions in the country which were at some stages very much exploding in terms of the contamination. There were others which were actually in very good shape. So characterizing, trying to characterize and to predict what is going to happen, it requires to be a little bit more precise and not to put all the country in the same pot. And in the same thing was I already indicated in a previous lecture with the development, let's say, of Poland after liberalization, which I will describe this. What happened in more detail, and also I showed you the map of China and the quotation of Deng Xiaoping that some regions will develop before others. That's a politically correct way to say that some regions will develop and some others will not. Or will develop only later, maybe supported by the other regions. So the model which I'm going to slowly describe to you and then describe what the model implies is that it does not take A as a single coefficient, but it takes into account the fact that in some places there is decay. Let's say A can be negative, and in some places it can be positive. And we are going to also take into account that this kind of A's, in place of being just a coefficient, in general they are in terms of some person being very bright and opening a new business and with a great idea, like Tesla had a great idea and invented the alternative current, and now his name is on these cars. Because of this, I'm going to take the A's. I call them discrete. Discrete in the sense that it's not a continuous. It's A in our case would be, first of all, spread over an entire surface, and secondly, it will not be let's say 1.75 to 69, but it will either be 1 or 0 or -1, and because in some places, if you just have one industry and that industry is collapsing, then you get -1. In our model now we'll have this, and already on the left hand of the slide you see the cover of this article, popularization article in New Scientist, where they discussed our model, and they called it ordinary miracles, because you will see that it has some conclusions which are very, very unexpected. Essentially, it shows that even if the general A is negative in a country, if there are some places where A is positive, that's already enough, because then those parts of the country will develop, and then they will probably expand their operations in the rest of the country. And let's say the example in Israel would be that the textile industry is going to shrink because it cannot pay enough money to the workers and also to the capitalists to keep that thing, because there is this competition from other countries like Bangladesh or other countries where the salaries are very low, and then the prices for the same thing is low. So you might have a shrinking of the activity, but on the other hand, you might hope that if the high tech is so much developing, then some high techs will move to the places where this textile industry is shrinking, and then have the entire country develop. So this is why we are thinking about these A's, not only that they are discrete, that they either are or they are not, but that they can move from one place to another. Let's say some high-tech industry moving part of its activity to the Negev. So the model which we are discussing would be that this is again from this New Scientist cover, where they described our model. And instead of K, from now on, I will call them B's, in order to emphasize that we are not speaking about the general capital of a country, but by a very localized industries or activities which can let's say multiply the number of firms in a country. Like in Poland, this is what we measured, the number of companies in a certain district. But again, I'm now discussing the in terms of economics, but as I emphasized at the beginning of the lecture, you can think also in terms of disease or of a political concept or of a viral movie or things like that. So symbolically, we are thinking in terms of this kind of situation that you have the A's, which are in the case of Poland, we found that it's the level of education in a certain location, plus B, which is let's say some capital which exists there, and then this kind of situation leads to the fact that you can increase the capital, increase the number of companies, because you have this kind of educated people which can which are able to conceive something new. So again, you see in my lectures, this kind of economic development is not seen in terms of some big companies which are exploiting who knows whom, but in terms of people which are thinking and creating new values, and this is how Schumpeter have taught about economic development. Now, in this New Scientist article, they called it angels and mortals because they thought of the A's in terms of angels and B in terms of mortals, and they connected it to some story from the Bible. This is not really correct to think in these terms. It was good because this New Scientist it's for more general audience. So not for peer scientists. We published it in the Proceedings of the Natural of the American Academy of Sciences. So. Of course, we didn't make this kind of comparisons, but in this New Scientist article, they did make this kind of comparison, which in some sense it's useful because it emphasizes again that the A's and the B's in this model are not anymore some A is not just some coefficient there, and B is not instead of K just some quantity of capital, but we are speaking here about what is called in technical terms agents, which means actors, so to speak, in which A's, as I said, are carriers of knowledge, and B are carriers of capability of developing something like a company. But still, I am adopting for some minutes this so to speak, metaphor of the article from New Scientist, and here there is an angel and this is a mortal, and then if you put them together, then you get the angels don't multiply, but the mortals do multiply in the presence of the angels. And as I said, we start thinking in terms of these A's and B's being spread on a map. You can, I take it in this model as a square map, but you can think about the map of Poland or the map of China. In fact, I showed you the differences between the presence of growth and of capital in different regions, and the absence in some other regions, both on the map of China and of Poland. The example of Poland will appear again maybe in this lecture, but definitely in the following lecture. So the way to express this is in terms of two things, and I think that already what I spoke now, we spoke last time. There is this lambda, life, giving life, proliferating, or in the case of capital is gain. So if you put an A and a B, then you get an A and B and a new B with some probability or some growth rate per unit time, lambda. But of course, the capital or the people can die, and capital can be depreciated. Like if you leave some machine in the field and do nothing, then after some years, it's not working anymore. Of course, if you are using it, then it also depreciates. So there is this coefficient which says how much of the capital or how much of the people are dying per unit time. So if you and from now I'm using this notation instead of thinking of k as something some growing. Now I'm not thinking about the individual bees as growing, but the bees multiplying. So for instance, in the case of Google, let's say, at some stage they split the company. Now I think that, and also Facebook, they changed the structure of the company because at some stage it is not useful to have under the umbrella of the same company so many different activities. Some of these activities will not succeed, and it's not fair towards the other activities to lose money of the entire pool. So instead of thinking of bees as growing, I'm thinking about the number of bees as growing, and because of this sign, I think it's called little grid or scale. I don't remember how it's called, but the point is that this represents the numbers of bees. So what is growing from now on is the number of bees, depending on the number of A's. So from now on, we'll have a formula which is of this type: the number of bees at t+1 at a certain location. It's the number of bees at the previous time minus the number of bees which are dying. So there is a certain rate of bees. If there are hundreds of bees, let's say 10 bees are per unit time are dying. But if it is 1,000 of bees, then it's again 10%. It's 100 of bees. So it's multiplied by how many bees were before, and plus the number of A's multiplied by this growth rate. So if there are many A's in a place, then the rate of bees growing it's larger, so to speak. If there are many high-tech capable people in a place, then there is a lot of new high-tech companies taking place. So the growth is proportional not only to lambda, which is a gain from 1A and 1B, but it's multiplied by the number of A's and the number of B's. So this is basically what this model says. And again, it's not for an entire country or the entire surface which I showed you, but for each particular location separately. So unfortunately, if if there are a lot of A's in the Tel Aviv area, but there are not so many, let's say, in some far away place, then you'll have a lot of growth in that area and less growth or not growth at all, or maybe because of the new term even decrease in the number of bees, in the number of companies, or in the production in some other region. So this is the kind of model which I'm going to describe. And I invite you to interrupt me, because right now I put in front of you the kind of model which we are going to study, and it is good not to go on before you understand this, what I said until now.
I would like to try to say what you said till now, and I will be happy if you can say if I understood till now, because I don't see. Okay, so I'm not seeing a lot of differences between what we saw in Schumpeter, the double exponential, and now, because the same mechanism is working.
I'm very happy you say that, because this was my effort to try to get you smoothly from the previous thinking to this thinking, but these differences which I just expressed, that the A's are either 1, 2, or 3, and the B's are 1, 2, or 3, and the fact that the A's and the B's on different locations are different, these two differences I'm going to show that they are very fundamental in explaining the reality as we see it, as opposed to the Schumpeter model, the way I explained before, which is a little bit too coarse to explain the details of what is going on. So if you think that this model is very similar to Schumpeter, then I'm very happy. It is very similar.
So the difference is that he is speaking like about closed system, and you're speaking about like open system, that the actors, the agents are moving from place to place. Yeah. So it makes it harder to say that a
Sorry, we lost contact apparently. Is anybody else hearing me? Because Gerson apparently his connection was lost. David Cohen, do you hear me? Yes, you made the sign that you hear me. So so it's not from my end, even though my connection is not very good either. They are promising that this country will go out of the third world in terms of communication, which is unfortunately was the situation until now. So we have very low connections. So let me be more precise. You see, if at a certain location there are no A's, A is 0, then the B at time t plus 1 will be just the B at time t minus whatever is the rate of death. So, however, if there is one A, then you will get the number of B's at t plus 1 will be 1 plus lambda minus mu multiplied by the number of B's at last year. And if there are two A's, then it will be 1 plus 2 lambda minus mu. So this is the kind of, and in a sense, this is answering the question of, I think Gerson was the one which was asking. So now we have the model is a little bit more complicated, but you will see that it's still relatively simple, and it is capable of explaining much more of the reality. Let me be even more explicit in terms of examples. Suppose that lambda is 3/2, and so there is some significant growth when A and B are at the same place, and the death rate is 1/2. Then the rule which I said is that at a certain point there is a certain number of B's, then you'll get 1 plus the number of A's multiplied by 3/2 minus 1/2. And in particular, let's say for A equals 0, you see that it's 1 minus half. So the number of B's are halving all the time. It's decreasing. If I had 10 B's at that place, then it's 10 divided by 2 divided by 2. Then next year I will have only 5 of them, and so on. And however, if there is one A there, then already it's 1 plus 3/2 minus 1/2. It's already 1 plus 1. So the number of B's will double. So indeed, this is what I wanted to show, that what we have seen in the case of Schumpeter, it's in a sense only generalized in a mild way by the model here, because indeed you see that if you have two sides, one with one A, one without A, then with 0 A's, then the one with 0 A's will halve all the time the number of B's, and in the place where there is an A, there will be double. So it's very much except that now we'll have more than two locations or two branches of economy. So and on top of it, there could be a situation where in place of not only that there is no A or one A, but maybe there are two A's. And in that case, the rate of growing of the B's is even higher. So another example would be that lambda is 1/4 and mu is 1/2. Then you would think that that is a bad thing, because the growth rate is less than the death rate. But now, because I can have more A's, then for A equals 0, I will have a decrease in B's, and for A equals 1, I will still have a decrease in the B's, because there is somebody which has the microphone on, and it's interfering. So please switch all the microphones. I think the one which has open the microphone is Muhammad had one, and please switch off. I don't know.
Go to the participants, then see what whose phone, not phone, the microphone is open, and you can push the button mute.
I don't. In principle, I think that I can switch off. Yes. I'm switching. I think. Yes, I think that I succeeded to switch off. But of course, it's better that each one switches off his own microphone, because I feel uneasy switching off. It's like infringing over the right of free speech of somebody to switch off. So it's better than people are polite and switch off by themselves. Anyway, I'm showing here that for certain values of lambda and mu, having just one A on one side is not enough to ensure the growth of B, but having two A's, it's also not enough. It just keeps the number of B's constant. So you need, in this case, three A's at one side in order to have the number of B's growing. So you see that this model is a little bit adding some complications, some additional structure as compared with the previous analysis, which I called Schumpeter. Poor Schumpeter didn't write this kind of formula, so I'm assigning to Schumpeter the credit and the responsibility, which maybe he doesn't deserve. Gershon, you hear me? Apparently he lost the contact, because I'm addressing him, because I understand that he was one which raised the issue of what is this model different from what we call the Schumpeter creation destruction model. But in a sense, it's the idea is there. Of course, as it happens many times in history, when we wrote the model, we didn't know about Schumpeter at all. But as I told you, I didn't know about Pareto either when we wrote about it. So this is how science goes. It's not always that we know everything which happened before. We are rediscovering things, but sometimes with a twist, as you see. So now, in fact, it's as Gershon said, if you had only two locations, one with an A and one without an A, one has a situation very similar with Schumpeter, sometimes, depending on lambda and mu, except that now I will show to you, first I will show that it's similar, but then I will show to you that sometimes, because X can move, then you can have more sophisticated dynamics which is happening. Like let's say it was as it was in China. First they wanted everybody to go to the Mao wanted everybody to go to the agriculture, because he essentially wanted the educated people to not interfere with his dictature. So he sent them to the agriculture and hoped that they will die there, which in fact happened. And after that, of course, the country, the economic was very bad, and millions of people died of poverty. So they allowed them back to the towns, and so to speak, the A was sent in one place and then in another place. So you can ask what happened. So in this graph, we are essentially returning to the kind of graphs which we had about the Schumpeter, except that now it's the number of B's which are the issue, and we are thinking in terms of A and B's. So for lambda equals 3/2 and mu equal half, as we had this example before. Then for A equals 0, you have lambda doesn't count because it multiplies to 0. So you have only dying half of the number of B's. So the B's are halving all the times. But for lambda equal 1, you have 3/2 plus minus 1/2 is 1. So it's a number of B's plus is doubling, because it's the whole number of B's plus 3/2 minus 1/2, it's 1. So in total, the number of bees are doubling. So if you think in terms of an A existing on the blue side and no A existing on the yellow side, then the total is going to be the number of the yellow is going down, the blue is going up, but the total is going down initially because I just started this way that most of the yellow was much bigger than the blue. However, if this situation continues, then the blues are increasing and the yellow are decreasing, but their sum is already starting not to decay. It stays the same, and the next time the blue is really doubling, and essentially the blues are becoming the new economy, and the yellow becomes negligible. So this is what we have seen in the previous cases. But as I said, now the A can change its place. So when we start, we are still getting the blue going up and the yellow going down. And the next time again, blue going up and the yellow going down. But now A can change size. So now the yellow is going to grow and the blue is going to decay. So the blue, as you see, is going down, and the yellow is not going down anymore; it's going up, and the sum is staying the same for this moment. But in the next moment, the yellow is doubling, and the blue is still going down, but the blue is not so important anymore. So you have a little bit of delay in this particular situation in the growth of the total, but eventually, so there was a stagnation because of the A changing. Like again, you can compare with the situation in China, where this kind of sending people to the agriculture and then calling them back. It was. In their case, it was more than a delay in the growth. It was a real disaster. So let's take another example. I'm giving all these examples because in a short while we will have a situation in which there are not only two sides. There are an entire region with many sides and with some A's going around and some B's being in each of the regions. And I want you to get accustomed with this kind of counting. This is instead of the very sophisticated mathematics which we applied to this model. But as you see, I'm able to avoid the mathematics and doing only the kind of arithmetics you do when you go to the supermarket and take into account how much bread you can afford and how much cookies you can afford and things like that. So so you can take now lambda equal 7/4 and mu equals 3/4, and in this case each unit time at each iteration, the B will be the old B is 1 times 7/4 the number of A's minus 3/4 the death rate. So in the case of A equals 0, if on a side there is A equals 0, then it's 1 minus 3/4. The number of B's are really decaying very fast. It gets 1/4 every time. But at a equal 1, you have 7/4 minus 3/4. It's 4/4. So it's doubling. And in this case, you can imagine that you have an A on the blue side and no A on the yellow side. So the yellow will go down by a factor of 4 all the time, as long as the A is on the other side. But the blues will double all the time. Now, pay attention that this looks like not a very good situation, because this is only increasing by a factor of 2, and this is decreasing by a factor of 4. So if you think in terms of if somebody, let's say an economist, is doing an average, then it says, look, half of the country is decaying by a factor of 1/4, and half of the country is multiplying by a factor of 2. So the average is going to be not very good, because the decay rate is far faster than the growth rate. But of course, the situation is not really like this, because at the beginning, indeed, the yellow, the all dominating is going down, so the sum is going down. But and here I'm thinking the A is changing size. So now the yellow will go up and the blue will go down. So the blue is going down, but now the yellow is going up. So in general, the economy is not anymore going down. It didn't recover really, but it's stopped going down. However, now we can think of the A changing again. And so this is indeed like having some government which went crazy and sending all the time all the people in the agriculture and then returning them. So now the A goes back to blue. So the blue will grow by a factor of 2 each time, and the yellow will go down. So meantime, the things are going only worse, because the yellow was bigger now, and now it went down. But of course, I'm not showing here what happened next. I'm now going to another example in which lambda is 1/3 and the mu is 1/2, which means that 1A is not good enough for ensuring growth, because no A means 1 minus half minus the mu, it's going to half. But even with 1A, it's 1 plus 1/3 minus 1/2, it's 5/6, which is going still, it's less than 1. In the case of corona, they say that the contamination rate is it's less than 1. So the number of bees are still going down. But with 2A's, if with one has 2A's, then it's 1 plus 2 lambda, which it's 2/3 minus half, which gives a total of 7/6, which is already larger than 1, so it's growing. So now we have this example in which there are 2 A's on the blue and no A on the yellow. The blue is going up by a factor of 7/6, but the yellow is going down by a factor of 2. So in general, the total is going down. This yellow is going down, but now I imagine that one of the A's is going to yellow. Now you see that what happens if I have two two A's on one side, then it's not so bad, because even if I start with a big yellow, the yellow will go down, but the blue will keep going up and will go up. However, if the two A's are equally spread between the yellow and the blue, then in both cases, I'm going down. Both sides are going down by by this factor 5/6. So you see, this thing is going down until when? Until one of the A's are changing, and then the side which has two A's is going up. So you see here something which is very, it's at the heart of the analysis, but very sophisticated analysis. The mathematicians which made this analysis, they wrote an article of almost 100 pages to prove that effect, that if you are taking the average A, like one A on one side and another A on the other side, then the economy is going down. While if you take into account that from time to time there could be more A's on one side and no A's on the other side, then you get that growth is still possible. So here is an answer to what Gerson said. In this model, if you take the average A over the entire system, in this case, there are only two sides, but you'll see the example in which the system is larger. If A's are uniformly distributed, then you can get an average A, which is not enough to ensure growth. While if you take into account the fluctuations in that some regions are just by chance with a larger A, then you can have growth of the entire system. So I'm showing this in a very simple way for a system which has just two sides. But this result is much more general. So what I'm saying here is that if the A's are jumping a lot and the B's are not jumping very much, then you have the average growth could be negative because of this situation. If the relevant A's are uniformly distributed, or if you are assuming that the A's are uniformly distributed, like in fact it is the case with this AK model. But as I told you, the mathematicians and the physicists ourselves, with some other techniques, have shown that if the system is arbitrarily large and the B's are moving and the A's are moving, then no matter how much A's are moving fast, so in a sense they are naively speaking averaging the number of A's. And no matter how small is the birth rate, so to speak, the lambda, and no matter how large is the death rate, the total B numbers is growing, at least in 1 and 2 dimensions. If you have a surface, let's say like the map of Poland and things like that. So this is why this article in New Scientist was called normal miracles, or something like ordinary miracles, because we have shown that in any system, this kind of miracle happens, that even if though, in naively speaking, the average number of A's is small enough and the death rate is large enough and the lambda is small enough, you might think that the total population of B's will go eventually down. We were able to show, and as I said, we had our techniques of theoretical physics, but also the mathematicians even had even more rigorous techniques, but they needed 100 pages to prove it rigorously. But the point is that in this kind of model, the bee population, the so to speak, the economy or the number of people or the number of individuals in a species, if you are speaking about ecology, is actually growing. Even though, according to the AK model or the Malthus model, the bee population would decrease, because there is this difference between taking the average bees and the average A's and taking the actual number of bees and the number of A's at different sites. You see, I put this S, which is that there is a dependence on the different sites. There are different bees and different A's, and this is a very important difference, which changes this equation between the AK model and also the in a sense the Schumpeter model, if you take averages, and the kind of models which we have introduced here. So I'm interrupting to invite you to ask more questions about whether I was clear enough about what is the kind of modifications which I have made to this naive model, in which A and K were taken for the entire country, and now is different locations, you have different A's and B's. Are there any questions? Okay, if there are no questions, I'm going to continue. Here are my co-workers in this article, in which we put forward this model, and we put forward this what this author in New Scientist called miracles. We showed this. Now this, especially Luzon and Bettelheim, they were graduate students, they were doctorants at the time, but now they are full professors, because not only because of this article, which was quite important, but also because they made other important contributions to science. So again, the guy said, new scientists, they explained that because of the fact that the A's are localized, then even if, though the population of the bees is dying in the places where there are no A's, in the places where there are A's, either one or sometimes more, the bee population can grow. Even in spite of the A's. So now I have a sequence of slides in which I'm reminding to you and make it more precise what is the model. And again, I'm able to express it in pictures rather than in mathematical formulas, which is very satisfactory for me, because I promised. It's not only that I promised, but it's also that I during all these years in which I I gave courses which were not easy to follow. Then I simplified more and more the way to explain it, and I hope that now I explain. So the A's can move from one place to another, and the B's can move from one place to another. And when the A's and the B's happen to be on the same side, then there is another B appearing, like in the case of animals, or people which are multiplying. But again, as I said, this is the case with the capital and with the capability of people to use the capital, the things which are their disposal in order to create new things. Of course, in the example which I gave at the beginning of the lecture, the people were able with their brains to create something like cooking gas or just out of nothing, of the garbage which people are creating, which is remarkable. But in general, you need a little bit more. Also, in their case, you need in order to make that container which creates cooking gas out of. It still costs something. I think that this container costs up to $4,000, and maybe because of this they needed a contract with the United Nations, because those poor refugees probably didn't have the money to buy this kind of container, and the guys which were inventing it, they weren't probably millionaires in order to be able to invest their own money in order to create hundreds and thousands of such devices. But the United Nations did have. So there is this. I'm sorry for that I interrupted the description of the model. So there was this multiplication, but there was also the dying of the bees. So this is all the B's are and the A's are doing. And now I want to emphasize that for the introduction of the model, giving some metaphor for the A's, for the roles of the A's and of the B's was maybe useful to animate them. But in reality, the A's and the B's are really not like angels and humans. They are more like molecules. They don't have any intelligence. The A's and the B's are moving completely random in this model, and the only thing which they are doing is that the B's are multiplying when there are A's around. They do not make any choices. They follow mechanical rules. They move in a random way. It's not that the B's are following the A's in order to multiply. And that's important to emphasize, that the individual B's are not following the A's. Why is it important? Because we'll see that the way the entire bee population grows is because there are some islands of the bees which are forming naturally around the A's, because in other places the bees are dying, so the bees are living only are being generated more than the death rate only when there are A's, and because of this, when the A's are moving, then these islands are moving too after the A's. So these are collective objects of bees which I'm going to show for probably some movies. Sometimes the movies are too heavy for the PowerPoint, and the thing collapses, but I hope I will be able to show you. And the point is that there is this unexpected situation in which there are new objects which are islands of B which are following the A's, but the bees themselves, each of the bees individually, they are completely blind. They don't have any intelligence, and they are not following A's. So I'm emphasizing that the A's and the B's are not following one another. They do not react adaptively to exploit the situations for their individual survival. It is only the population of the bees which are surviving more than you would expect from the average models of the type of AK model. So you'll see that there is what we call an emerging collective objects which are adaptive. That is the kind of realization of some idea which was going around the mind of the physicists which are involved in this, about the emergence of adaptive objects which are surviving because they are adaptive. But what is adaptive are not the bees, are the collective islands of the bees, and we'll see this. So this is yes. These black things are the A's, and the B's are multiplying. This is inspired by the kind of illustration which was made by the author of this cover article about our model in New Scientist. And this is another thing. We have shown we have this movie. It's about a situation in which one single A is enough to grow, to have growth. So you see that there are the locations of the A's, and then in those places the B's are multiplying, but in every other place they are not multiplying. And again, if the A's would be spread in a continuous way about the entire surface, then there will be no growth at all. Everything would be left essentially this rose background, which is essentially zero B's. So you see that in a sense, it's not good to have inequality, but if you have a choice between not having anybody surviving and having survival in some as I expected, this thing has collapsed, and I'm going to charge it again.
So if I understood correctly, it's like evolutionary process.
Exactly.
And when we saw the bees following the A's, it's not because the bees always follows the A's, but because the bees that not following the A's, we not see them because they are disappearing.
Yes, exactly. Oh. And in this respect, what we made a remark is that in this model there is a certain correction to the what's his name? The guy which invented the evolution, Darwin. If there is a correction to the Darwin, because in Darwin thinking, there is this adaptation of the animals to the medium. But in this case, there is an additional thing that there is that the animals are choosing the medium. For my preferred thing is the following: suppose that you have a population of rabbits, and there are places where it's good for the rabbits. Let's say there is a lot of cabbage there, and there are places where they are not good for the rabbits. Now, in the places where there are no good for the rabbits, the rabbits which were there, they are either dying, and I prefer to speak about dying because, as I said, I'm not taking into account the fact that the rabbits can go places where there is food. Even if the rabbits are completely stupid and they are just dying in the places where there is no cabbage, there will be rabbits in the places where there is cabbage. And then the new generation of rabbits, lo and behold, they are born in the places where it is good for them to be, because in the places where it's not good for them to be, there are no parents to generate them because they died. So the new generation of rabbits are born in places in which are good for the rabbits to live, because there are cabbage there. So in a sense, there is enough that there is some place where it's good for the rabbits to live. Then in those places, there is the rabbits will prosper. And in this respect, you'll see that it's the same with the capital. You don't need intelligent capital it's enough that the capital in place, which is invested in places which are not good which are not good investments, it's lost. However, in the places where it's not lost, then there will be more capital and there will be more development. So, for instance, as there was this example which I gave about this chips, electronic chips. Investing in chips, in electronic chips, gives a lot of profit, and then there is more capital invested in chips. And this is how you had this Moore law, in which every couple of years then the density of elements per chips was doubling. This is the Moore law. So I'm not showing again these movies because, as you see, they are breaking the system. But I'm going to this explanation. So the number of A's, the concentration of A's, it's random. It's random. So in some places there are no A's, in some places there are one A, and in some places there are, this red thing. I think that you can see them, in which there are two A's. So in other places there could be more A's. And in those places where there are a lot of A's, just by chance, there are these islands of B's which are growing. In fact, this is a logarithmic scale on this side. So when you see red, it's not just that there are just a little bit more B's. There are a hell of a lot of B's, as in fact you have seen in the movie before. So there are these islands and of B's which are formed in the places in which just happens so that there are more A's. And of course, if the A's would be moving very fast and on a very small surface, then you would have an average A, and that average A wouldn't be good enough for the bee population to survive. But because of this situation in which locally there is this exponentiation of the number of bees, then you have this kind of adaptive islands which are following the A's, as you have seen in those movies, and this effect happens. So this is again a movie. And again, I think that it's going to collapse, yes. So I'm going to again the thing. Wait, just a second. Okay, so I'm loading it again, and I'm sharing again the screen. I'm sorry for these delays, but I knew that these movies are pretty heavy for the PowerPoint environment, and it's bringing them down from time to time. Oh, I covered a lot of material today. Okay, so I'm not giving anymore the movie because but essentially it shows how if I start with a certain population of bees, in most of the space, the number of bees is actually going to zero. But there are these islands, adaptive islands, which are following the ace and which are not only surviving, but in fact growing exponentially. And in this article in New Scientist, in fact, he showed a lot of, he went to many other scientists to ask if they see this kind of effect, and he has, they told him, yes, in different subjects, that there is this effect that naively you would think that a certain species in an ecology doesn't have any right to exist because in most of the places it's not growing, but just by chance in some places it's growing, and they are surviving. So in the case of economies, these sites on the lattice are like locations, but you can also interpret them as not locations in the real space, but in big sectors, different sectors in the economy. And in fact, nowadays they have maps in which different technologies and different products are neighboring one another according to whether they can be, by changing a little bit of technology, you can go from one product to another. And the bees can be capital, but in the case of Poland, we counted the number of companies because the money wasn't very stable in those times. So counting it in terms of money or dollars, it wasn't correct. And the ace, as it turned out, there was in the case of Poland, it was the level of education of people at that location. But of course, there are other things which are important. For instance, if the different agents have the freedom to decide what to do, because in some communist countries, as opposed to what is China today, they realize from time to time that the economy is bad, so they would allow some people to open, let's say, a little restaurant or something like that, because the restaurants which were kept by the state were awful. But those restaurants were very quickly growing because they were, kept by people which were free to invest there. And then they would hire helpers because there were more clients than just one person could serve, like the owner. And then the Communist Party would say, "Oh, you are exploiting those workers." So they closed those restaurants. So there was this kind of tango in which the state would realize that the state-owned companies or restaurants or whatever it was wasn't working. So they would allow people to do something privately, but then they would so successful that they would start hiring helpers. Because there was more business than one person could serve, and then the state would say, "Oh, but we are a communist country; we cannot allow you to exploit guys." Even though, of course, the guys which were working for the owners, they were very happy to work for the owners because they would get more than they would get from the state. But that was beside the point. It was against the ideology. So this is why I wrote freedom here. And of course, there is also a matter of trust. If the state would nationalize, like in many states, they decided, this belongs to our nation, and those capitalists from the West are exploiting our wealth. Let's nationalize it. And of course, they nationalized it, and in most of the cases, those nationalized companies were not working anymore very well, and in fact, there is this example of Zimbabwe, which was a very prosperous country for a while, and then they started to nationalize everything, and they became the poorest country in the world, basically. So this A and B model, it's taking into account implicitly all this phenomena. There are various interpretations, as I explained to you, to this kind of B's being multiplied in terms of A's. For instance, if you think in terms of chemical molecules, that the A's and B's are chemical molecules, then the spatial patches are like the first cells in which life appeared. And then it gives you some intuitive metaphor about how life can appear out of simple chemistry, because of this adaptive islands, which you can think about them as the beginning of cells. And there are other examples, but I don't want to get into too complicated explanations here. So what happens is that next Sunday it's a holiday because of the Hanukkah, and so there is in principle no lecture, but I will appear on the as usual on the internet and answer questions. So in particular, if there will be questions about this other understanding of the AB model in terms of how species appeared and how the immune system works, then I can answer that. But I can answer also any other questions. So I will show up at 12:30 next week, and I will wait, let's say, for a quarter of an hour if there are questions of people which want to discuss anything. And if not, of course, I will not stand by for 2 hours, but everybody is invited to.
If there is no others, I will be happy to speak with you.
Yes, perfect. So I will be online next week.
Wait a second. You speak about next week, not now.
Not now, no.
Okay. So let's see.
Now we have 2 minutes left, and I was just discussing the fact that in principle.
Yeah, I heard, but I saw that I thought that you're done, and you are saying that you are staying now.
I'm staying now, but I will not be very efficient because I don't know about you, but after 1 hour and a half, my brain is a little bit overheated. So of course, I'm willing to answer questions, but not in a very massive way. One more comment about the implication of this AB model about capital. You see, Newton, there was at the time of Newton a kind of bubble because the king gave some company the right of a monopoly on the trade with India, basically, and with other countries, but India was very important. So there was a bubble, and he, of course, he thought that this is madness to invest after so many people, because there was no reason for that. But at certain stage, he thought that in spite of his reasonable approach, everybody was gaining a hell of a lot of money by investing in this company. So he invested too, but by that time the bubble burst. So he lost a lot of money, which it's about the equivalent of today, 20,000 pounds. But he was a professor only, and so he didn't have a lot of money. So he was pretty unhappy that he lost this money. So he said, I can calculate the motions of having bodies, because this is his great discovery, you know, the planets and the way they turn around, but not the madness of people. And now this model shows that financial markets do not need wise or intelligent investors in order to work, because it's like with the situation with the bees. The bees are very stupid, and they move randomly. They don't choose where there is A, so the place where the capital can grow. But the market can be very efficient even like that, because in the places which are not efficient, then people invest money and they are lost. But there are some people which just by chance they invest in the places where the money is not lost. And that money grows, and apparently it's good enough for the bee population, according to our theorems. It's good enough for the bee population to always grow. So in a sense, this relates to the Adam Smith invisible hand. Even though if you don't take the investors are very intelligent or even self-interest, the capital has this capability because of the self-generation about this multiplication. It grows just like that even in random environments. Even when you think that in general, in average, the growth rate of the economy would be negative. It's actually very resilient. That is the point. The resilience of things which self-multiply, whether it's species or ideas or viral concepts or capital. So in a sense, even I personally am not very interested or admirative of capital. This model shows that there is something special about the capability of capital to self-multiply. It gives a lot of vitality to the economy. So it's 2 and 3 minutes, so I'm stopping here. And as I promised, if there are questions, I'm willing to answer them.